Now this figure is showing electric and magnetic field moving together, and it follows the Ampere's current law in antenna that is producing a magnetic field. You can see from this figure, and the relationship between electric and magnetic field shown at one instant. So as the current varies, the magnetic field varies in magnitude and direction. So this figure is showing that the current in the antenna produces the circular magnetic field lines. You can see here these circular lines is showing that the magnetic field that is producing here, and the current produces the separation of charge along the wire, which in turn creates the electric field. So the electric and magnetic fields E and B that is near the wire are perpendicular to each other. They are shown here for one point in space. The magnetic field varies with current and propagation away from the antenna at the speed of light. So the magnetic field lines also propagates away from the antenna at the speed of light, forming the other part of electromagnetic waves. You can see from this figure B. So the magnetic parts of the waves has the same period and wavelength as the electric part, since they are both produced by the same moment and separation of charges in the antenna. Now you can see from this figure the electric and magnetic waves are shown together at one instant. The electric and magnetic field produces the long straight wire antenna are exactly in same phase. Now note that they are perpendicular to one another and to the direction of propagation, which is making its transverse waves. So this is a very important thing to note that here. So a part of electromagnetic waves sent out from the antenna at one instant time, and electric magnetic fields are in phase and they are perpendicular to one another and in the direction of propagation. So clearly the waves are shown only along one direction, but they are propagate in other directions too. So electromagnetic waves generally propagate out from the source in all directions, sometimes forming a complex radiation pattern. A linear antenna like this one will not radiate parallel to its length. For example, the wave is shown in one direction from the antenna in figure. So instead of the AC generator, the antenna can also be driven by the AC circuit, and the charge radiate whenever they are accelerated. But while a current in a circuit needs a complete path, an antenna has a varying charge distribution, forming a standing waves driven by AC. The dimensions of the antenna are critical for determining the frequency of the radiated electromagnetic waves. This is a resonant phenomena. When we tune radios or TV, we vary electrical properties to achieve propagate resonant conditions in the antenna. So you can see here that why we study electromagnetic field. EM principles find applications in various allied disciplines such as antennas, microwaves, fiber optics, electromagnetic interference, bioelectromagnetics, radar meteorology, satellite communications, electromagnetic devices, which includes transformers, telephones, transmission lines, waveguides, antennas, and optical fibers, radars, lasers. So many applications of electromagnetic waves and why we study electromagnetics. So it is very important part for our daily life. And this course is distributed such as the electrostatics part. We will talk about the electric field and the flux and the Poisson equation. This is del square psi equal to rho upon epsilon naught. And magnetostatics, we will talk about magnetic flux density and magnetic field intensity, where we will talk about Ampere's law and the time dependent fields, that is we will study about Faraday's law, and we will talk about the waves, The Maxwell's equations, we will talk about the all Maxwell's equations and their derivations.